Takashi is Assistant Professor, Faculty of Applied Biological Sciences at Gifu University.
Hello everyone, my name is Takashi Tanaka from Gifu University of Japan. Today I'm going to talk about the topic Rethinking Experimental Design and Data Analysis for On-Farm Experimentations. Before starting to talk about the way how we should analyze on-farm data, I'd like to briefly summarize the process of OFEs. Principally, the process of OFEs are almost the same as the general scientist experiments. The first step is to set our hypothesis. For example, whether new products such as fertilizers or chemicals are effective on your own farm. The second step is to design experiments. We have to consider how to set replications or randomizations of the experimental plots. The third step is to run experiments and to collect data. This step is basically managed by farmers. And the fourth step is to analyze on-farm data using statistical modeling. And finally, we can discuss and review the outcomes of OFEs with farmers if there are still questions to be answered. We need to repeat this process. So in my presentation, I mainly talk about how to design experiments and how to analyze data for OFE. As I mentioned in previous slides, the objective of OFEs should be clear before running experiments. And now let me get this straight. As a result of the OFEs, the statistical analysis will provide two information. The one is whether our treatment is statistically significant or not. We scientists are always regarding this significant effect of differences as important, since it becomes a kind of evidence that we want to demonstrate. The statistical significance is generally determined by probability, and the significant level is typically set at 5% for scientific research. So note that the value 5% is just based on scientific perspectives. It may not reflect the farmer's practical significance or interest. Now, only significant tests would not provide information to whether the tested treatment is economically beneficial. So what farmers and practitioners want to know is the quantitative effect. For example, it can tell us how much grain yield could be improved by the treatments. And it's meaningless for farmers if the cost of the inputs were higher than the profits, and although the treatment significantly improved the crop yields. So we have to remind that the significance, not only the significance, but also the precision of the quantitative effects should be paid attention. Actually, there are many types of OFEs based on the practitioner's assumptions and expected outcomes on application. The OFEs can be largely classified into two types. The first one aims to assess the overall effects. The final goal of this approach is to adjust or extend examining specific treatments on the entire field. Strip trials like this picture is the most popular experimental design. In other words, variable rate application technology is not always necessary to implement this type of OFEs. So from smallholders to broad acres farmers, regardless of farming scale, every farmer can join OFEs if the yield data is available. The overall effects depends on assumptions that crop response to a certain treatment is constant within the field. But this assumption is too strict to apply for large fields, so another type of OFEs has been proposed, which aims to quantify site-specific crop response. Like this picture, productive zones can be delineated within fields, and each management zone may have different crop response to the specific treatments. Final goal of this approach is connected to variable rate application. And in this presentation, I'll mainly talk about the experimental design and data analytics for evaluating overall effects through OFEs. To evaluate the treatment's effects precisely, the design of the experiments is the most essential step. And so many agronomists and statisticians says replications and randomizations are the principles of experimental design to improve the precision of experiments. This picture shows the several examples of the experimental design to compare the effect of treatments and control. The complexity of the design increases along right side. Accordingly, the outcomes of statistical analysis is expected to be more precise as well. but we need to keep the experimental design as simple as possible, especially when the variable rate application technologies are not available. The most popular experimental design is the strip trials, as shown in the middle of this picture. And later, I'm going to discuss whether these strip trials are recommended or not. So these kind of strip trials have been used for a long time because of the simpleness of the way. This picture shows an example of corn hybrid selections in North America. Yield data was collected using weight wagons, which means total weight of each strip represents sample observation. And the total weight is compared by using conventional statistical model like ANOVA. But of course, weight wagon won't tell us the spatial variations in crop yield. And now a lot of farmers now using yield monitors in Western countries. On the other hand, UAV and satellite remote sensing is becoming popular worldwide as well. And needless to say, remotely sensed data itself only indicates the plant health, but many studies demonstrated that grain yield or quality could be predicted from the imagery analysis. So substantial spatial observations can be made using sensing technologies. At the same time, this spatial data is problematic for analysis, for data analytics, and I'm going to talk about it later. All right, now I'd like to begin to discuss the best experimental design for OFE while referring to the work by Alesso 2019. This paper examined the effects of replications, randomization, and statistical model types on the estimates bias through simulation study for corn production. Let's take a look at this figure. The vertical line of RMSE beta hat shows a kind of indicator of estimates bias for the treatments. So the smaller value is, the estimate becomes more precise. And horizontal one corresponds to the size or the number of the replications. And as you can see, this kind of chessboard design shows small bias. And interestingly, the best performance was found in the strip trials with smallest experimental units. The biases increases along with the size of the experimental units. So concerning about the first question, whether we should repeat or not repeat, the answer is that replications are absolutely needed for OFEs. And next, I'd like to see the effects of randomization. In this figure, solid lines represent the systematic design, while broken lines represent the randomized design with the same replications. According to the results, randomizations did not contribute to reduce estimate bias. On the contrary, randomization increased the bias. So in conclusion, practically the best experimental design is systematic strip trials with so many replications. And here new questions will be arising. Everyone says 3 replications enough for the analysis, but it may not be promising probably. It's very difficult to generalize the minimum number of the replications for the strip trials only from these results, and it may depend on the case. To make sure the required number of the replications, a simulation study is very helpful. So if you have raw yield map, we can simulate the best experimental design, potentially having the less bias for your own fields. And if you are interested in simulation studies, please refer to these papers. Okay, now let's take a look at the slides explaining a statistical model for OFEs. For a long time, classical statistical models such as ANOVA or t-test have been used for the data analysis, but classical statistical approaches assumes that the observations are spatially independent. Moreover, sample size collected by yield monitor or remote sensing is so huge that increases the risk of the false positive or estimate bias. Only the design is not always sufficient conditions. So spatial linear mixed model have been used for the solutions for analyzing on-farm data. Spatial linear mixed model can estimate treatment effects precisely by conducting residual spatial effects at the same time. To compare the precision of the statistical outcomes between conventional and spatial linear mixed model, we simulated to conduct on-farm experimentations for wheat with 5 different experimental designs. This is a bar plot showing estimated mean values of a treatment's effects and those 95% confidence intervals. In this simulation study, wheat yield was set at 0.3 ton per hectare higher in treatment plots than control plots, as indicated by this green line. As you can see, classical ordinary least square model, which is a synonym of the ANOVA or t-test, showed large estimates bias and narrow confidence intervals. On the other hand, spatial linear mixed model showed a mean values close to the actual treatment effects, while the 95% confidence intervals becomes large when the estimate had large biases. So the main points that I'd like to make in this section is that the classical statistical model could gives you wrong estimates more frequently and even result in adverse scenario like design 2. Here I present further important notice for data analysis. As shown in this heat map, yield data show different spatial trends according to the directions. This case shows that short and higher yield variations across the rows rather than along the rows. This phenomenon called anisotropy, which sometimes increases the risk of the estimate's error. So anisotropic spatial model should be used if you find anisotropy. In addition, prior knowledge should be considered in designing experimental plots or performing data analysis. For example, specific row effects often has extremely high or low yields due to the overlapping of missing strips. And boundaries of land consolidations or under drain pipes sometimes appears as crop marks. So historical yield maps or satellite imagery and field observations are informative to identify such noisy hotspots on locations. Practitioners should avoid to use such locations for designing experimental experimental plots or exclude from the analysis. Or such prior knowledge could be treated as explanatory variables in spatial modeling. So here now I'm showing you a lot of available software packages to perform spatial modeling. And here this GeoR or GStats, very useful packages for R. And now I'm also developing spatial linear mixed model, which can account for the anisotropic model in MATLAB environments. Today, I didn't touch the topic of the site-specific crop response, but a lot of studies are using SPGWR packages for R. And in addition to the on-farm trials data, if the other data sets such as soil properties or elevation map are available, machine learning approaches may contribute to work very well for optimizing prescription maps for variable rate application. So finally, I'd like to summarize the main points of my presentations and to show remaining issues to be solved. We must keep in mind that conventional experimental design and statistical analysis may potentially have large estimates errors. Replications are needed, and spatial modeling is also a promising approach to avoid unreliable estimates. And today I only talked about how to deal spatial data to get robust solutions, but there is still a big problem of dealing with the temporal variations. The objective of OFEs is to optimize the crop management practices, so it's sometimes too difficult to repeat the same experiments for a long time. Every year, OFEs may show the different outcomes even in the same sites. So to get through the problems emerged from the temporal variations, data aggregations among farmers or crop modeling approach should follow OFEs. And that's all my presentation. Thank you for your attention.